Good morning, everybody. As I had mentioned, we are going to talk about multi-agent systems for emergency response. This is joint work between a lot of organizations. Syed and I are both from Vanderbilt. Um, this work, we collaborate with Washington University in St. Louis, Stanford, the Institute of Software Integrated Systems, which is at Vanderbilt. Part of this work was sponsored by the Center of Automotive Research at Stanford. It's also heavily sponsored by the National Science Foundation and our partners at the Tennessee Department of Transportation. So what I'm going to start by doing is give a very broad introduction to what the emergency response problem is from the perspective of, say, computer scientists. Why are we interested in this problem, and how can multi-agent systems, which is a subfield of artificial intelligence and data-driven modeling or machine learning, can alleviate some of the problems in emergency response. So why are we sort of interested in this problem? So this is a very old newspaper clipping. It goes back to the early 1930s, and it says that the large sort of population in the United States was very worried about the total number of people who were dying of motor vehicle accidents. So it's been almost 100 years now, and so you would imagine that this has largely been dealt with, but it turns out that it's not the case. In fact, this is a very recent newspaper clipping. It says that about 30,000 Americans or 30,000 Americans die every year, or at least it projects, due to motor vehicle accidents. The real number is actually much higher. It's close to 40,000. But if you can read the article, it's especially the last line, it says that car crashes are the #1 cause of death for Americans under 35. As far as largely the youth of the country is concerned, this is the leading cause of death. This is a map of Tennessee, which is where Vanderbilt is, and we collaborate a lot with first responders and the Department of Transportation. Every dot, every green dot that you see, the fluorescent green dot, is a motor vehicle accident. And essentially what you see here is practically everywhere there's a road, there's been an accident. This is aggregated over the last decade. So that's how serious this problem is. And it motivates us to look at this problem from a more principled perspective. But there are other forms of emergency response that we care about as well. And we'll briefly talk about those forms of emergency incidents as well. And one of them is poaching. So this is an article which mentions that between 2013 and 2016, 100,000 elephants were killed in Africa. So, I mean, you might want to pause and ponder over that number. That's 100,000 elephants in a span of 3 years, largely to supply ivory to illegal markets. And these are also sort of discrete events that happen in space and time, much similar to accidents. There are obviously ways in which poaching and emergency incidents differ, like traffic accidents differ, and we'll explain that as well. Also, this recent issue that has come up is this really shy and elusive animal, the pangolin, is being hunted to extinction because of its demand in the illegal medicine market. And oftentimes, issues like this subsume other incidents. For example, illegal fishing often subsumes child labor. Now, we are also interested in emergency response to wildfires. Now, if you've been on the West Coast, or for example, in Utah in the United States, or we have seen wildfires recently in Turkey and Greece, you know how big this problem is, and it's only projected to increase. Every year, there are thousands of acres in the United States that get burned due to wildfires. And the cost of destruction of life and property and of rebuilding is often staggering. It's in billions of dollars. So we want to understand how emergency responders can use data-driven modeling and principled decision-making to better respond to wildfires. Now, this is an overview of the broad pipeline that we deal with, and this is a very high-level overview of the research we do on this project. We do everything from designing methods to sense, detect, predict, plan, and act. So we want to sense and detect where and when incidents happen. We want to predict them so that we can plan for them or plan in anticipation of them proactively. We then design planning modules, and we also look at principal ways in which how emergency responders can respond to incidents or act so as to respond to these incidents in an efficient manner. And there are a number of challenges. So large multi-agent systems are extremely complex. There are agent-based interactions. The environment in which these systems are deployed are complex. There are short-term dynamics like traffic, weather, and events. For example, there could be sports events in cities that affect the distribution of these incidents. There are also long-term environmental dynamics that change. For example, there could be a construction in some part of the city, and that might completely alter the way traffic accidents happen in the city. But there are also challenges with resilience. For example, if you deploy a fleet of responders to respond to incidents, what happens when communication infrastructure breaks down, which could happen, for example, in the case of a wildfire or in the case of hurricanes. Or equipments could break down. For example, you could design planning system, assuming that you have 20 or 25 responders, but if some of them break down or are out for maintenance, how can your AI planning module adjust to such changes in the environment as well as in the space of the problem? So here are some of the broad technical challenges that we face, and I'm going to highlight these challenges, and then we'll actually go about discussing how individually we can address each of these challenges. So the first challenge is that we deal with extremely large and highly multimodal data. So for example, the analysis of wildfires, the project that we do uses billions of data points created from satellite imagery. For example, in the case of accident prediction, we use granular traffic data, which is massive. So think of a measurement coming from every road segment of your state every 30 seconds. And this comes in real time, so you have to process it and ingest it as it comes. You have to update models and make predictions. Although I have mentioned, and this might seem a bit counterintuitive, I mentioned at the beginning of the talk that accidents are sort of ubiquitous. But when you look at accidents from the perspective of, say, every day or from very short time periods and very high spatial resolution, they're actually quite sparse. Most roads during most times of the day don't experience accidents. And most places, thankfully, are not on fire most of the time. So we have to deal with extremely sparse data. There are large forms of uncertainty. One of the big forms of uncertainty is state uncertainty. So for example, how can we allocate a limited number of agents to stop a rapidly moving wildfire, especially when smoke prohibits observation of the fire? So we don't know the underlying distribution, the underlying state of the fire, but we still have to allocate agents to respond to that. And this is a form of state uncertainty. The state isn't fully visible. There's also communication uncertainty, which I briefly alluded to in the last slide. So disasters can cause communication failure. So we are interested in answering the question, how can multi-agent systems work if the agents cannot communicate or have very limited communication? I briefly mentioned about poaching, and poaching introduces adversarial effects. So for example, if we know where poaching is expected to occur and if we deploy ranges there, then the poachers will move. So how can we solve interactions in multi-agent systems that basically take the form of games? And finally, these environments are highly dynamic, which means that what if we learn a really complex model for emergency response and deploy them, but then some event happens in the city and completely changes the dynamics of the problem? Do we have time to relearn everything, or can we readjust things in an online manner and quickly deploy something? So we have done a bunch of work on all the different problems that I briefly mentioned: forecasting, allocation, dispatch, robustness, online update and modeling, and also deploying these large-scale systems. We'll start with forecasting, which Syed is going to cover. After that, we'll have an invited talk about incident detection, which is not included in the pipeline, but is a very important component. And Hemant will give an invited talk about how we can use social media data to better respond to emergencies. And then finally, I'll talk about allocation, dispatch,